Okay, here we go. This is Chem26DBlake. Finishing up this chapter review. We had talked about some of these for an old and a stock system naming system. Number 94, name each molecule. SeO2 is selenium dioxide. Its new name is selenium 4 oxide. B is SeO3 is selenium trioxide. Its stock system name is selenium 6 oxide. Let's give this one a try. It's SeO3. All right, this is not a polyatomic ion. The charge has to add to 0. That's one of the oxidation number rules, by the way. It's probably rule 7. Rule 8 on this table. Sum of them, then a neutral compound is 0. And this one says rule 9, the sum of them on a polyatomic ion adds to the charge. So I have 3 oxygen, -2, -2, -2, and something for selenium has to equal 0. Well, you ought to know that +6 -2, -2, -2 gives you 0. So the oxidation number is -2 and +6 for selenium. So its name is selenium 6 oxide because that's the oxidation number of the selenium. That's not hard. That is not hard. I have students that act like it's hard. Probably shouldn't be giving birth if something is hard, so we're not going to learn it or not going to do it. I guess giving birth seems kind of hard to me. Okay. If that's the criteria by which we decide things. C, N2F4 dinitrogen tetrafluoride. It's nitrogen 5 fluoride. If you're using the stock system name. And S4N4 tetrasulfur tetranitride. Nitrogen is over there in the take 3 column. Its oxidation number is usually -3. Since these match, it must be salt. It must be 3 sulfur. If you have a question about the oxidation number rules and how to use them and how to get these names, let me know. We'll work a couple examples. Every book is good aspects and bad aspects, and this one gets to oxidation number rules way late in the game. So 95. Formula for each molecule, sulfur difluoride should be SF2. Silicon tetrachloride should be SiCl4. Carbon tetrafluoride is CF4. Sulfurous acid is H2SO3. Let me know if you have a question over one, if you want to go over those acid rules again. It seemed like we did that in class, went over it again, and it seemed like you're okay with it. Okay, 96, write the formula for each molecule. Silicon dioxide is SiO2. That's a major component of glass. Silicon tetrachloride, SiCl4. Whoops, I'm on the wrong thing. 96, bromous acid, HBrO2. Chlorine trifluoride, CF3. When you get into these halogens, you might be, ClF3. You might be confused about what goes first. The least electronegative thing goes first, the more electronegative thing goes later. And chlorine is usually the more electronegative 3. But it is with fluorine, which is the most electronegative element on the table. That's why its oxidation number is always -1. So fluorine is -1, oxidation number. Chlorine is +3. So in the stock system, the name of this would be chlorine 3 fluoride. Okay, and this is hydrobromic acid, HBrD. Okay, next one. 101, draw 3 resonance structures for the polyatomic ion CO3 2-. Okay, First, you want to draw the Lewis structure, which comes out like this. Okay, you add all this up, you get 24 electrons. By the time you add 2 extra on, I think you end up with 24 here, so you have to take a pair out and move a pair. And you end up with a double bond here, but the double bond could be here, the double bond could be here. So what happens is you use valence share electron pair repulsion theory, which means you're not going to have 90 here and 90 here and 180 here. They're going to spread around. And this whole thing shares a charge, so it's 2 minus. So because it is a polyatomic ion, you put the whole thing in brackets. You don't use brackets for molecules. You use brackets for 2 reasons so far. One we've discussed. One, if it's a polyatomic ion. So you use a bracket, bracket, bracket. The other reason you use a bracket is to include everything that does resonance. So the bracket has 2 completely unrelated and separate meanings in this example. So we have chlorine, chloride, and this bond has double bond character, but this bond has double bond character, and this bond has double bond character. And this bond behaves, or this oxygen behaves as if it has some partly negative charge, and this oxygen behaves as if it has some partial negative charge, and this oxygen behaves as if it has some partial negative charge. It's often described as, you know, the molecule or the ion is acting like it's going back and forth very quickly between multiple states. That's not an accurate representation, but you'll hear that. It's that those bonds and those charges are shared in molecular orbital, which we're going to talk about more in organic chemistry, and each of those has some of that character. So we draw it all 3 ways with an arrow showing that it kind of could go back and forth. And because it does resonance, big bracket around my 3 resonance structures. And that bracket doesn't have anything to do with these. What you don't use a bracket for is a molecule. Some of you were putting brackets around your molecules on Lewis structures. You don't do that unless that molecule, you're showing that it has resonance. And then it would have a bracket on either end, not around each one. Technically, that's wrong to do that. Okay, Lewis structures for these molecules, each of which has a central atom that does not obey the octet rule. PCl5 has 10 shared electrons between it and chlorines, and we could draw it this way. Okay, by the time you add these all up, you should end with 40. You have to have an extra chlorine, and this is called an expanded octet. Next one, BF3, is less than an octet. Everything in the boron family will do that. Let's go back to this. So, argon has an octet. Noble gases have an octet. That's why they don't do chemistry. There's some weird exceptions, but it has to do with expanded octet. Halogens form an octet. Oxygen family, they form an octet. Nitrogen family, they form an octet. Carbon family, they form an octet. So all those end with 8. Boron family end up sharing 6. Alkaline earth metals end up sharing 4. Alkali metals end up sharing 2. If you put hydrogen, for example, with anything else in this table, they'll have 2 electrons shared between them. Those are called hydrides. Now, in some of these families over here, if you go down off the second level, we'll talk about this in organic chemistry. Well, we're going to talk about it now. You can't do it in the second level, but if they're in the 3rd level or beyond, and they can take electrons out of a d orbital or put electrons into a d orbital, they can do expanded octets. And there's other exceptions besides what we've discussed. Okay, but BF3, they're going to end up with 6. This is called a suboctet. Boron's going to end up with 6 shared pairs, and that's kind of its Lewis structure there. ClF something, 5, expanded octet. Putting chlorine in there. Oh, this one would be too hard to figure out. It has a lone pair off this chlorine. You about can't do this one unless somebody tells you how to do it. When you add all this up, you should end up with 42. So basically you got 8 times 1, 2, 3, 4, 5. You still need 2. And so you're going to put an extra lone pair on that chlorine. So chlorine actually is sharing 2, 4, 6, 8, 10, 12. Chlorine can do some pretty strange stuff. Okay. BeH2, beryllium is in. Remember, whoops, this is not what I wanted to do. Octet, 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 octet. Ends up with 6. Beryllium, these guys end up with 4. 2 shared pairs. So you would just end up with this BeH2 hydrogen on either side. HCO3 minus. They're all 2 resonance structure. Okay? So what you have to do is carbon, hydrogen, oxygen, oxygen, add them up to 18. Draw a Lewis structure. You're going to have to remove a pair and move a pair. And that oxygen pair could either be off this, or that double bond could either be off this oxygen or this one. And that partial negative charge could be off this oxygen or this one. And these are going to move around, so it's not 90 and 90 and 180, but they're going to move around, so it's about 120, 120, 120. It'll be a little more here, a little less there. Well, that double bond could be here or it could be here. So you have a resonance structure to show that it could be either at the same time. And that negative charge goes here to show that it's somewhere on this polyatomic ion, and you can't pin it down. It's going to have some negative character here and some negative character here. So it's as if we're going to say, even incorrectly, that it could be this or both, all at the same time. And then, so we got brackets around this because it's ion, and then brackets around that because it's doing resonance. And you can tell you're doing resonance because you have the double arrow. I didn't point that out last time. Okay. Lewis structure for a molecule of these compounds and ions. H2S, it's just like water, H2O, the sulfur's right under water, so you're going to end up with the same thing for the central atom. BF4 minus, boron, you're supposed to end with not an octet. Remember? So it's always something different. Usually you're supposed to end with 6. So it's an exception to the exception. Whoops. But if you just punch in what they got, put your 3 here, you add it up, you got 31 plus an electron gives you 32. Put boron in, put a fluoride on each side, put the shared pairs in, give everybody 8, and it comes out. It ends up being not so bad, but actually this would be easier if you forgot about the 3 almost. Okay, so the whole thing is an ion, so we put the bracket in with the charge. Remember, if it's a molecule like this one, no bracket. 104C, sulfur dioxide. I think this one does resonance, but I don't have a resonance structure drawn for it. Okay, so 18 electrons, and you wouldn't have to, by the way. If you drew it and you ended up with this, I'll call it good. You don't have to have the resonance on it if I ask you for the Lewis structure. Okay, that's what it ends up. Well, this is the Lewis structure. This is after you apply valence shell electron pair repulsion. So I'll take either one of those. Okay, and SeCl2. Put the Se in the middle. Gotta have 20 electrons, you just end up with this. Okay. And 105 says, which elements in the list below are capable of forming molecules in which one of its atoms has an expanded octet? Well, nothing in the second row can do it. So boron, carbon are out, oxygen are out, P and Se can. Because they're in the third period or greater and they're over there on that side. Okay. Quiz.